This conference will now be recorded.
Okay, it's a little bit of a sort of a light-hearted thing when I started looking at Newark Flat Crossing and doing the presentations about it. It was basically that 16 noses, 36 legs, but can't walk. It was just a question I posed for people to start thinking, well, what the heck is he going to start talking about? But anyway, basically, Newark Flat Crossing has basically those attributes, but obviously it's just a way of actually introducing the actual flat crossing itself. This is obviously something that was carried out last August bank holiday in 2019, so a little while ago, but still relevant in terms of some of the technology we introduced for that particular renewal. So for those who don't know about Newark Flat Crossing and aren't familiar with the area where it actually is, there's a map obviously in front of you now showing what actually the layout looks like. It's clearly on the East Coast main line, north to south, and then the Lincoln to Nottingham line, east to west. Obviously intersecting there without any switches, just lots of crossings that actually allow the two lines to cross each other. So it's got a 44.1 degree angle between the two intersections, which is quite unique in terms of junctions in the UK for infrastructure and network rails maintenance requirements, because it's the only one of its kind in the country of this type that's such high speed. So the actual speed across the crossing is 110 miles an hour. Either side of it, it actually moves to 125, but the crossing itself is 110. And that's a view of what it looks like on the ground when you're next to it. Clearly quite a lot going on there. And on the right hand side, there is a picture of one of the cast crossings as they are manufactured by Progress Rail currently, to look at any replacements that are needed for this in terms of maintenance or renewals. So obviously there's a bit of history here because this crossing's been around for quite some decades. Obviously the history behind it really is, I think, the actual different railway companies in the times when there was various different companies operating different lines had to agree that one was going to cross the other, because they both were run by different companies initially. So obviously a bit of a conflict of interest in some respects. So initially, this is obviously going back some time. Some old photos that one of my colleagues actually put together, where we're talking about how it was installed, obviously 1960, maybe what you people would term about modular joints that we currently have now within S&C. Maybe it's not such quite a new idea considering what it shows in this particular photograph. And then later on in 1972, it gets replaced again with Jarrah packings. So lots of different mechanisms of different, I suppose, technologically advances as you're going through from different renewal stages. Then in May 1986, it started looking a bit more like it does currently, with renewal happening again, with some 13.6 meter hardwood bay beams in this case. And then obviously during the electrification of the East Coast Main Line in 86 to 88, that made things a little bit more awkward when it came to renewals in future. So the last one that was carried out prior to last year was in August 2003. And as you can see with the huge Ainscough crane that is there, that was how they installed it in the particular renewal at that stage. And as you can see with the wires that are going through by the actual crane, the overhead lines were in the vicinity, so they had to be raised out of the way to make sure that the railroad crane could actually install the flat crossing in a one big lift, as you can see there on the bottom right hand corner. So in this case, the actual change meant that the actual timbers themselves extended a little bit further than initially, at 16 meters, and that's the size they are currently in terms of length of the timbers and what they're supporting on the crossings. Then I got involved in the Newark Flat Crossing some time ago, because I used to work in the S&C team within the what was Safety Technical Engineering, which is now the Technical Authority. And we had to look at some of the crossings and redesign and replace some of the crossings due to some issues, which we'll talk about in a minute. And obviously, at that time, an 80 mile an hour speed restriction was in place due to the issues which we'll talk about shortly in the deterioration of the passing systems. So summary, in what happens in Newark Flat Crossing, it usually has an intervention to renew it, or has up until last year, every 15 to 20 years, depending on the asset condition. Track quality, even after it was renewed, is quite often goes straight back to poor or very poor band. That's down to various issues, which again might become clear a little later on in the presentation. The ballast had degraded below the sleepers, in other words, the timber bearers that were on, and that got to the stage where the ballast was basically past its sell-by date, so to speak, and that was confirmed through the track bed investigation team's work that we'll go through shortly. And the double star crossings, each of those were on a maintenance requirement to actually go in there every 8 weeks and inspect them and carry out any remedial repairs. So they're quite heavy on maintenance requirements due to the actual layout and how much real impact forces occur on the crossings themselves and how much deformation occurs. So they're quite resource ready, heavy on maintenance requirements. And at the time in the renewal, or up until the renewal, a couple of years prior to the renewal happening, the timbers themselves are starting to deteriorate to a point where one of them at least was getting to the point where it was not going to be able to last very much longer. And obviously a TSR was probably going to be imposed if the renewal didn't go ahead. So this is a specification basically of the timeline of what we actually had to work through to get to the renewal in August last year. So the life expired asset was something that was going to be replaced in year 1 of CP6. And basically the first meeting was in February 2017 about looking like a like-for-like replacement of currently what was there before the renewal took place. I had a few issues with that, but I didn't know about this until later, and I'll go through how I found out about this because I wasn't involved in the actual work for putting together a plan for what was going to be changed. Again, I'll go back into a bit of detail about what that entails a little bit further into the presentation. In November 2017, we started looking at introducing FFU, which is a fibre foam reinforced urethane product, composite material effectively, for longitudinal timbers. So basically for going over bridges where we've got problems where timbers are actually decaying and we need to actually replace them with something a bit more long-living component that helps reduce the maintenance costs due to issues for long timbers. So an acceptance certificate was put in place on a trial basis for longitudinal timbers to be produced and installed with FFU. FFU was used during the trial for about 4 or 5 timber bridges down on the southeast, as it was, to see how much performance benefits we could actually see from using the FFU and introducing it. So in December 2017, the composite bearer option was something that was put on the table from potentially discussions with L&E, as it were at the time. Then 2018, it got to a situation where we got acceptance to put the timber, the balks in on timber bridges, but it was decided by some engineers at the time that it weren't fully understood as to how this material would perform to actually allow us to actually look at putting it on Newark Flat Crossing. So in March, there was more conversations with the RAM track for Eastern region as they are now, L&E as they were at the time, that composite bearers basically shouldn't be considered because they couldn't actually guarantee what the robustness was, and they wouldn't know how much time, considering the effect of using timber bearers, how much the FFU would actually last in terms of giving any benefits cost-wise. However, I looked at this in 2018, about February time. I found out about the renewal that was being planned. And I was a little bit unhappy in the way things were going because they were trying to actually look at potentially a like-for-like renewal, which, as we'll become clear later there are some issues that would have happened and caused lots of issues maintenance-wise if it was carried out in the like-for-like terms, as there were some problems with the crossings, as I found out within 2015 when I got involved with the Newark flat crossing for the first time. So I basically pushed to try and get acceptance with the head of track to say we could actually look at a design for using the composite FFU option and look at how we can actually make that work, which thankfully I got backing for that. And then when we went back to the RAM track, and he actually looked at the issues we were discussing with them, and obviously then took up the option to actually get Sekisui, the manufacturer, to look at putting a suggestion together and a proposal for how this could be done. And then in July of 2018, Progress Rail got the actual order for making the bearers alongside the rest of the whole unit. So this is the 2003 drawings that we were using initially to look at what the design of the actual bearers should look like. So the bottom drawing is the one that was used, which was basically copied and pasted into an FFU version of what you see there. So the drawings themselves had to be modified to suit the FFU design and how we'd actually put it together, but that was the basis of what was used to look at how this would be installed. For those who know a little bit about Newark flat crossing, you can see just a little bit on the left-hand side of that bottom drawing, there are some anchors that were actually planned at the time to actually hold the timber bearers in place. Those anchors didn't actually get installed in the 2003 design, but obviously that was the situation that they were seeing some way of actually trying to anchor everything down to stop any movement occurring. So back in 2015, I got asked to look at assisting the route with a problem with broken fasteners on the actual crossings themselves. As you can see on this photograph, you've got a slight different angle to the crossing foot where the screws go in. This is a 1 in 20 angle, which was decided to actually be the design from 2003. So effectively what they were trying to do with either side of the crossing was pin it together, so it was going to restrict its movement. But by 2014, nearly half of the screws in the whole layout had actually failed. Basically, you can see on there are some holes, obviously, where the screws would actually have been in position. And the problem we had was basically the ferrule that you can see on the top two that are together without a screw in them is made of plastic. And that ferrule was obviously installed as part of the fastening system for the 2003 renewal, but it was a piece of the fastening system which was quite susceptible to wear. And that means when we got some lateral movement, when trains pass over the crossing, the movement laterally tries to obviously push the crossing out. The ferrule and the screws would rub against each other, and over time that would wear, allowing a little bit more gap in the diameter between the actual casting itself and the actual screw. And that just perpetuated further and further. The gap got bigger and bigger as the wear between the screw and the ferrule increased. And the problem was they couldn't actually take the screws out and replace the ferrule because the green heart timber that this was made of initially is such a dense timber, you can't actually undo screws very easily. The grip that it has on the screws is so tight, you would end up shearing the screw just trying to take it off. So the problem you've got here is the lateral movement had caused the screws to start breaking. They've broken down into the timber itself area, so the top part of the screw would come off. But because again, we actually had a real tight grip on the actual screw itself, they couldn't actually easy out or drill out the actual remnants of the screw to replace it with a new one. So they were stuck with a fastener that couldn't actually be replaced. Hence, we've got a big problem because, as it says there, nearly half the screws had failed by the time we actually got into this situation. So L&E at the time looked at this solution, which was going to be something they were hoping would be a stopgap to keep the unit going until such time it got to a point where it was actually able to be renewed. It was a nice idea from the start of it, but it was never going to work. It was fraught with problems in terms of how you could install these clamps and obviously maintaining the toe load on the crossing foot. So yeah, it looked quite entertaining when you went out to see this when it was actually installed, but basically it lasted about 3 months before these started to fail. So I got involved and looked at how we could actually help get the foot redesigned to a vertical angle to prevent the lateral movement being a problem, and allowing the crossings to be installed without actually having this issue to be addressed in years to come once things had actually started wearing. So that's basically how we redesigned the actual foot itself and the screw system fastening to replace the crossings across all 8 to actually get these to be something that was actually more durable. So effectively we actually looked at EDH in these crossings as well at that time, so that's explosively depth hardened the nose and the wing rail where the wheel transfer took place, which had not been done on these crossings before, and that just gave us some resistance to plastic flow when wheels started actually going over the crossings as new, because obviously anybody who knows a bit more about austenitic manganese steel, that it's relatively soft. So when it's actually starts seeing wheels going over it, it needs to have a period of time where it work hardens, and during that time the actual profile changes because it is quite soft initially. So it's a bit like basically you could argue it's something like a piece of plastic being pushed by a finger, if you like, very, very broadly speaking, but that's what happens to cast manganese crossings when they're actually not EDH'd and installed in track before work hardening begins. So just going back to the fastening system, on the left-hand side you can see the 2003 arrangement where you've got the 1 in 20 angle, which was trying to pin the crossing in position to avoid it moving laterally. But because they've got the nylon ferrules in place, it was an area where it wasn't understood that those would start wearing, therefore lateral movement would start increasing, and then obviously that would take its toll on the actual screws themselves. So in 2015, in the center there, we redesigned the actual casting to allow us to modify the fastening systems to a point. Money was an object because the route were obviously going to pay for all these at the time, and we weren't really able to design it fully to what we would say was an optimum situation. So we had to allow for the casting to have an eccentric ferrule, which is this particular item here, which meant that any position where these holes were drilled for the screw, we could actually put the eccentric ferrule in there and turn it to a position where it would actually meet the hole center that had been drilled by hand. So it could actually make sure that this fastening system was tight, the screw wasn't allowed to move laterally, and because this was made of steel, the ferrule didn't have any possibility of wearing. We still, as you can see at the bottom, there was quite a wide hole still there for the original steel plate, which the screws had to go through, but the crossings have sat on, and then the pad that goes on top. So it wasn't ideal because we still had that gap. But after about installation of about 2 years, all the fasteners are still intact. So it was tantamount that actually the fastening system had improved dramatically, considering the situation they were in, with 45% of them being in a failed situation in 2015, 2014. So moving on to the 2019 design, we looked again at how we could actually reduce the amount of components we need for the fastening system and how we could actually improve its fixity. So in other words, there wasn't any lateral movement possible to allow the screws to take the toll of reducing the forces and lateral movement that was possible. So we took the ferrule out, reduced the size of the diameter of the screw hole in the crossing foot, and then did the same to the plate. So everything was very much more tighter tolerances to allow the screw to be screwed into the actual top of the timber and keep it all in place. So that's what's currently installed on the crossings that were installed in 2019. So basically these are the changes that we actually put into the renewal itself. So obviously the biggest one was we actually introduced FFU material for the bearers instead of using green heart timber. The reason behind that is a bit more than just the requirement to actually look at something that's a bit more durable. You'll see later on there was an issue with being able to obtain Greenheart timber if that was what was decided was going to be the actual reason why we actually changed that timber into that material. We did a bespoke Trek bed design, which again we'll talk about shortly. HP rail, high performance rail, which was a product from British Steel, as they're a French owned company now. But basically that was to allow us to have a similar high hardness rate on the actual crossings because of the EDH, mated up with a rail that's going up to the leg ends with a similar hardness level. So there wasn't any dissimilar hardness between the two sections of rail, and we didn't get any plastic flow on the actual normal heads size rail coming off the crossings. We used then also introduce SG cast iron base plates with Pandra Lee plus clips, so gave a much higher toe load than the PR clips that were actually used in the 2003 renewal. Concrete sleepers and bearers with under sleeper pads on the run-on and run-off of the crossings. We also looked at optimizing the crossing profile with doing a study with Huddersfield University. That didn't quite give us the answer we were hoping for, and we knew it might actually be a bit problematic because if you've got optimization of the crossing profile on north to south route, it might then cause problems for the east-west route because of the profile not being optimized for the running of trains going across the east-west side of the Nottingham-Lincoln line. So if we did the opposite and optimize the Lincoln-Nottingham profile crossing noses, then it would basically give us a problem going north to south on the East Coast main line. So there was a bit of a trade-off into what we could actually achieve with the actual profile of the crossings themselves. But it was worthwhile actually studying that to understand if there was some advantage to actually change the profiles. But we basically decided to leave them more or less as they were. And the crossings are pre-drilled for continuity bonding, when I get the words out. Just something which would just save time actually on the installation. So, okay, we'll look at what was the reason why we went for composite as a material. So these pictures here, you can see these are the bridge timbers that were actually installed on some of the southeast bridges over a trial period that the introduction of a few started. Obviously, looking at the actual track construction standards, it does say that composite artificial timbers should be considered for longitudinal timber renewal. Now, we knew flat crossing obviously isn't a longitudinal timber bridge, but it's a similar scenario in terms it's a long timber that is supporting the crossing and supporting rails. And the reason why it's actually on there is obviously because of the wheel contact loading that actually the crossing layout will actually see every time a train goes over it. It needs to have that continuous support to make sure we don't have any problems with the track quality or reduce the actual effect that might have. The other reason why we had to look at an alternative was the bottom here. We obviously looking at route services to supply the timber. They went and had a look at what the market could offer. But obviously, as you read there, Cameroon was the actual lumber mill location that we would actually get our timbers from in this case because of the way the route services contracts are set up. But they were actually in the middle of a civil war, so trying to get the timbers themselves would have been a bit problematic, and it would have taken up to 2 years to try and get them and source the right length. And the other problem was, as you can see there, any timbers over 6 meters in length would have been very difficult to actually obtain. We needed 16-meter lengths, 8 of them. So there was a big problem in terms of being able to guarantee the supply and making sure that timbers would be available to actually allow the renewal to be built before we actually got to the stage of actually installation. So because of that, that main problem, it was decided that the FFU solution was basically the one we'd have to go for because there was no real guarantee that we could get any timbers of any type that would actually be suitable. So the option of FFU was basically not forced upon us, you could say, but it was the best option to take to guarantee we could actually meet the renewal. So FFU, fibre reinforced foam urethane. As I said before, it obviously was initially given trial acceptance to put on the bridges just to understand how much performance benefits it could give us. But what is FFU? Well, that's obviously the name, fibre reinforced foam urethane. And that's the manufacturing process that Sekisui, the manufacturer of the FFU material, carries out to actually give you, or the customers, us in this case, the required length and the required section of whatever material you're looking for in terms of FFU requirements for a timber bridge in this case. But obviously there are limits to the actual manufacturing process, which we'll mention in a minute. But ultimately it's a pultrusion process where it uses glass fibre reinforcement, and then it's actually impregnated with foam urethane to give you the actual finished product. The challenges of looking at how we could introduce this was, when we introduce a new product, we've got to go through an assessment of how much risk we're introducing to the infrastructure by introducing that product. And we've got to put an application then into Network Rail Applications Panel, NRAP, and classify the actual project as whether it's actually significant or non-significant in terms of CSM, Common Safety Method. For those of you who aren't familiar with Common Safety Method, it's a very rigorous risk assessment process we've got to go through and complete to introduce anything that's going to change issues on the actual infrastructure and introduce new risks that perhaps aren't currently known or aren't currently managed in the way that we need to. So the problem we had with this one was that as the renewal organisation was going to replace it more or less in like-for-like terms in terms of the design of what the actual layout looks like. In other words, if you look at what we've got now, it doesn't look any different in terms of geometry or position as it was in 2003. So in terms of what the renewal organisation were looking at, it was deemed as non-significant because they weren't actually changing anything from their perspective that would change the way that the installation would have to take place. However, when it came to myself leading the project to actually get the bearers changed to FFU, then that was a change of material, and it was a unique configuration for the material as well. So from a product point of view, it is very significant. So I had to put in an application to say, from our point of view of an engineering perspective, technically this is a significant CSM project because we are changing a novel material, introducing a novel material, I should say. So they agreed with my classification. So we had to do the full Common Safety Method risk assessment process, go through all of that. But the problem we have with that is we hadn't done much in the way of CSM with STE leading it. So that was a new area that we had to get our head around of what we needed to do. And also the renewal organisation didn't have any experience in doing CSM either, because the CSM aspects of any renewals was done by the asset enhancement area of renewals. So IP had a particular project team with asset enhancements who looked at all the Common Safety Methods requirements. The normal delivery organisation, so the Central Rail Systems Alliance in this case, they didn't have that experience, so nobody was fully au fait of what we needed to do. So we had to lead the process ourselves with help from Ricardo Rail, who were appointed as the ASBO, independent assessment body for the project. Sekisui needed design approval. We had to get that in place by December 2018 to make sure the timescales worked for getting the actual bearers in the country to be able to actually get the layout built in time to make sure it was fit for being installed on that August bank holiday last year. So we as STE led this design approval process and looking at how we actually needed the RAPW drawings to be produced from Sekisui's manufacturing drawings. And we needed some bespoke arrangements for the product acceptance because of the requirements of the FFU material. The size of the bearers needed were also a bit of a problem for us because of the available sizes that Sekisui could make in Japan, where they actually manufacture the FFU material. So that was the issue we had in terms of their capacity of the machine that they use in Japan to produce these could only produce something up to 9.4 meters, but we needed something that's 16 meters long. So obviously quite a shortfall there. And the problem we had also was compounded by the fact that if you looked at a shipping container, maximum length you could get in one of those was only 10 meters anyway. So that was another initial problem of actually getting exported FFU bearers from Japan brought over. So the solution, we actually looked at talking to Progress Rail and saying, well, okay, we need some help here because we can't manufacture these in Japan. They're not going to be long enough. The capacity of the machinery in the Japan's Sekisui factory doesn't give us the 16 meter capacity that we need. So we looked at what solution we could put in place for this, and that was then looked at, well, okay, can we actually build these in the UK by Sekisui providing the machinery or the technology in the FFU material to allow them to be built to 60 meter lengths. They said it was possible. It'd never been done before. They never had any situation where it had actually been built outside of Japan, but it was possible. So we went into discussions with Progress Rail to look at seeing if they could help us by actually facilitating the build of these bearers. They got the contract for the whole layout anyway, so we asked them if they could actually build the bearers in one of their facilities. After discussions, obviously Progress Rail looked at initially and said, well, we don't build bearers, we build crossings, we make switches, we build layouts, we don't build bearers. But obviously we went through the issue of how this could be done with Sekisui in detail to understand what was possible, and Progress Rail thankfully rose to the challenge, and at their facility in Ilkeston, we got everything shipped over from Japan to allow them to build the bearers in their facility at Ilkeston with technical support from Sekisui engineers. Sounded straightforward, but one of the other issues which has come out of the woodwork at the time was Sekisui engineers very experienced, but they didn't speak English. So we had to get a translator, or Progress Rail had to get a translator to make sure that we could actually get the technical detail needed and the support from Sekisui to the Progress Rail guys to help them build the short bearers. So looking at this diagram here on the left-hand side, the dark orange sections here are the actual sections that were built by Progress Rail. And the lighter orange ones were built by Sekisui and shipped over to the UK to allow a bit of pre-assembly to be actually carried out to reduce the amount of work that's needed in the UK. And this is one of the top drawings of the layout that was basically put together by Sekisui, is how the actual construction would need to be taken place and what sections were needed. There were 17 of these particular drawings, so quite a lot of detail needed to actually be worked through to make sure we got the right result at the end of the day for the layout to be built. So just moving away from that for the time being, we'll look at the track bed in terms of what was needed for this to be looked at from the foundations, if you will, upwards. So they looked at how they can reduce ballast settlement, reduce maintenance interventions, and hopefully reduce possibility of track geometry faults. So the TBI system investigation looked at on-site measurements, looking at also doing a finite element analysis and modeling of what they found, and looked at how a computer model would actually show them what the actual design and indicate what the parameters would need to be addressed and how that could be done. So lots of high dynamic forces, obviously, over the crossings themselves, causing lots of wear on the ballast itself. But they found the existing geocells that were actually underneath the crossings were still in a good condition, so that was a positive. But looking at the degradation analysis of looking at possibilities of how or what options we had to replace the bearers. Obviously, looking at the left-hand side there, looking at the current condition, the ballast settlement was quite high, obviously looking at maybe up to 20 millimeters. If we change that to just new FFU, then over 30 years, they predicted that obviously we'll get something like a little bit less, about 15 millimeters of settlement. We then were actually looking at considering whether we put under sleeper pads on the actual FFU bearers themselves, which obviously brought the ballast settlement potential down even further. And then looking at how compacting the ballast, the bottom ballast itself, would actually help potentially as well. On the right-hand side there, you can see the analysis of what the actual ballast settlement rate might be, depending on the option taken and how much more life you might get out of the ballast compared to just leaving it in its current condition. So the FFU with unsleeper pads and double compaction was the best option to take, looking at the actual modelled percentage of improvement. And this is a schematic of what the design looked like, of what was actually happened. So the existing GSL layers there, that wasn't changed, but they decided that adding another new GSL layer, but extending the actual layer out to into the transition area, was going to optimize the best ballast bed option for this. So that was carried out, and the ballast system itself was expected to be much more resilient to reduction in ballast life. So a lot of work done by the ballast team, the ballast investigation team, track bed investigation team, to get that design modelled and assessed, and then obviously put together. With talking to IP, obviously there was a bit more of a compromise needed, because on installing what they actually designed was probably going to be quite difficult. So there are some challenges to face to try and look at what's the best optimum they could get for the design, considering what the modelling was suggesting. So this is what was actually installed, where the new GSLs went over the actual crossing area, and obviously into the transitions going at either side of each of the crossing legs. So now we're going to how we actually supplied and manufactured the whole layout, mainly obviously focusing on the bearers themselves. So as I said before, Route Services placed a contract with Progress Rail Services to carry out quite a lot of work, supply the new double star crossings with EDH, exploded depth hardened surface, get them to subcontract with Sekisui to supply the actual FFU bearers and build them in the UK, with obviously support from Sekisui engineers. And then looking at how we can basically look at maintenance and how they would actually take this forward into their control once they finish, so how they actually need to look after the view in terms of what maintenance it needs. The PRS also assemble a complete layout itself at their one of their sites, deliver it and reassemble it line side with assistance from the Central Rail Systems Alliance, and build all the external panels, including the adjustment switches and slave panels needed for the renewal. And also do a bit of the subcontract with Huddersfield University to look at the actual profile optimization of the crossings. So this is the actual FFU itself. So if we just go around the actual pictures on the left-hand side at the top there, that's what was delivered and what it would look like to Progress Rail from Japan. The bottom left, there's some jigs, obviously holding it all together, and laminates. So this is in 30mm thick layers, which were then glued together and clamped into the correct shape that was needed for the whole bearer system. So on the middle photograph there, you can see the different beam sections and the cutouts where these would actually be installed into form the lattice of the whole bearer unit. This is obviously just a picture of that being placed in position. On the top right hand side, you can see that obviously the final layouts, bearers in place, not fastened together yet, but just in place to actually show what the actual layout looks like in terms of the actual footprint of the bearers made out of FFU. So quite a lot of work went on to actually get this and achieve the actual result here. So moving further down to the construction of the whole layout, adding the actual pad on the left-hand side for the crossing with the steel plate underneath it. You can just see the rusted sections of the steel plate that you can see that where the cutouts are for the pad in this area. Cross-section of the cast manganese crossings, and obviously how they're fastened down in terms of positioning, just to get them in the position they need to be for the actual layout to be completely assembled. And the base plates here, we've got a raised UVC check plate, which was designed, not quite bespoke, but it was a design for an R56V check plate that was modified to suit what was required for the check plate that Newark flat crossings have. And there is the obviously the whole layout assembled without actually being fastened down at the moment, but it shows you exactly what it looked like in the yard of us as it's been completed by Progress Rail. So, and there's a timeline on the side there of how it was actually built. So quite a lot of work done in quite a short time. One of the problems we had that with moving the actual layout, everything had to be stripped down again from the site at Ilkeston and transported to Beeston where the railhead was, and then obviously loaded onto the tilting wagons, as you can see there, to take to site. But one of the issues we have with the FFU in this situation is we didn't know what the bending moments would be like for the sections themselves. In this case, they're not too heavy in terms of the big overall weight, but we had to put something in place to make sure that we were careful with how we loaded these, because of any twisting or any bending of the beams would be catastrophic, because they'd obviously only got enough material to build these once. So we had to be extremely careful as to how these were lifted and handled to make sure that we weren't putting any undue stress or any damage on the bearers themselves. And where we've got the joins here, we had to be extremely careful when actually assembling the bearers together again, because if you damage these joints, then obviously that could cause a big problem when it comes to the installation itself, and maybe reducing the life of the bearers if we actually caused too much damage when they were trying to put them together. And obviously the adjustment switches, which we needed obviously either side. One of them was quite unique in terms of its structure, which was not really, going back a bit, not really something you could see physically, but one of the actual adjustment switches was vertical. All the others were inclined because of the situation we found on the site. Because further down from the crossing themselves, there's a new crossover that had been installed, but because of that was vertical installation for the S&C that was butting up against the adjustment switches, it was decided that trying to actually make it, turn it back to incline and then to vertical again in such a short distance was impractical. Therefore, one of the actual adjustment switches was made as vertical set, which hadn't been installed on concrete before, and that caused some problems later on, but perhaps another discussion another time for that. And on the left hand side you can see the actual slave panel that had to be built bespoke for the requirements to be able to get the rail levels in the hole that was left once they actually taken out the old crossing and put the track bed down. The height of the crossings as they were installed meant there was a need for this bespoke panel to be built with timber sleepers 3 times the height to allow it to fit properly. Okay, looking at the plan for how the renewal was actually going to be installed. Trying to keep things as business as usual as far as possible. Site build area had some constraints and the land requirements that we needed to build the layout out up on site. Cranes were used instead of a mobile crane because there was obviously advantages that we didn't need to take the OLE down. They could have functioned and operate underneath the OLE. We had lots of limited space because some of the land that was available for us and owned by Network Rail, it was sold off by our land team within Network Rail, and obviously caused quite a lot of problems because of the access we needed. Using the curved cranes obviously meant that we didn't have the issues that you might have with high winds and using a big Ainscough crane like was used in the 2003 renewal. And if necessary, if one of the cranes failed, there was a possibility, and within the actual lifting capabilities, one of the curved cranes could actually lift the whole layout and put it in position if needed. So there was a bit of contingency there if failure of one of the pieces of kit did occur. Thankfully, that didn't happen, but it's a possibility, so we had to actually cover that one. Removal of the old flat crossing. So the castings that were installed in 2015, they were all retained and kept, and some of them were, I think, were actually sent to Whitemore, the S&C recycling facility we have, for storage to allow the crossings to be utilised for spares in future. Obviously, temporary track panels had to be created when they had to be actually looked at how that could be delivered to track and installed as and when the plan needed. Looking at the difference in heights between the adjacent and plane line of the crossing area, which just mentioned, looking at that slave panel that's 3 times the height with the sleepers, slave rails themselves, and then clamps obviously to join the slave panels together to allow the cranes to move backwards and forwards over the layout when needed. And the bonding of the crossings themselves, as we talked about initially with some of the tasks that were talked about before. And how the handback happened, because there is a cord on from the Newark side to the East Coast main line that allowed trains to travel around slightly to get back onto doing some train movements on the main line between Newark and King's Cross. So this is basically a lifting plan of the old crossing. So obviously the green there is the old crossing itself being removed, and the red and the blue are different sides, obviously, but these are strapping points for actually lifting some of the panels out. So that was obviously quite a detailed plan of how to take the crossings out because of the complexity of the renewal. The panels that were actually going to be installed to allow the renewal to take place, and how that would actually need to be planned when each panel was going to be installed and what order they were put in. And as I said before, this is the panel that was needed to have the sleepers that are 3 times the height of a normal sleeper to allow the rail height to marry up to the panels and the crossing. You can see there on the top there what the actual height difference looks like and how they actually worked out using 3 deep sleepers for the panel would actually give the rail height the right distance to allow it to meet up without too much problem. So lifting the new crossings. Now, the changes of the position of the centre of gravity of the layout proved some challenging situations when you'll see some of the photos later on when we actually started moving the crossing. So this was the plan where 2 Kirov cranes would actually attach to the crossings in the positions you can see there. They would then lift it so it's parallel with the track, move it over to a holding section in the top north of the layout crossing corner there in preparation for being able to lift it into the hole. And the reason why it was put into a holding section was because there was a slave panel had to be put in place here to allow this blue Kirov crane to travel across the hole that had been left by the taking off the old crossings. So once that had been put in place and they'd actually laid the new panel down, they had to remove the slave panel out of the way before they could actually lift the panel into position. So obviously there's quite a bit of prep work needed before we started doing the renewal. And that was basically this area here. You can see where the actual layout was built up. A lot of this land had to be flattened and a lot of aggregate laid to allow it to have the flat area which was required for the layout to be built on site. Now, as you can see, that actually caused quite a lot of problems because the amount of spoil that was actually laid down, you can see the height difference here between the actual ground and the top of the section here where the build started taking place. So you can see it here on the top right there. as to where the actual layout was rebuilt after being transported to site. And obviously a lot of work had to go in to allow that to be prepped in 3 weeks before the actual layout was installed. This is obviously the unloading of the panels as they're transported by train to site, and reassembling them, putting them back together in terms of forming the actual bearer matrix which was needed for allowing the crossings to be built on top of the whole structure. And then obviously the layout itself was built back up with all the geometry requirements and crossings, etc., to actually fasten everything down. And Rob Kitchen, who's on the call, he can see his own autograph there, look. So one or two others obviously decided that they'd add their little bit of graffiti to history before the installation. And ultimately, once it had been completed, that's what it looked like, waiting to be installed. I had a bit of a heart-in-mouth moment by the guy who was leading the team, Kev King, to actually, from Progress Rail, to look at this. I went over to site and had a look at this as it had finally been finished. And he took me one side and he says, "Oh, I've got a bit of an issue here. So that I've been eyeing this up, and I don't think it's going to fit. I don't think the angle's right." And it's one of those moments where you've got your heart in your mouth thinking, is he right? Just for a millisecond. And I thought, no, of course he's not right. The crossings are at the right angle. They're exactly the same crossings that have been installed before. And this is from the castings that have been done over many, many years and replaced. So they fit. So the layout's got to be the right angle. It can't be incorrect. And luckily enough, there was no problem. It's just one of those areas where you're thinking for a millisecond, hope he's not right. Okay, so it's going to actually the delivery of the renewal. August Bank holiday happened to be the day of the renewal itself where it was installed, the hottest day of the year, about 35 degrees, which added to the problems of how we actually go about installing this. So there you can see quite a few different photos of different setups of sections of removing the old crossing. And there are quite a lot of problems trying to get them out. As you can tell, the actual bears themselves were quite well embedded into the ballast, even having dug them out to actually get access to the full bearers and then cut them apart so into the sections that they actually used to lift them all out of the hole and get everything out of the way for the renewal to actually take place. Bit of more photos of the geocell being put down for the run on and run off to the transitions. A few more photos just looking at ballast obviously being put down for the bed before we started putting the panels back in. And then we started lifting the crossing. As I said to you before, looking at how this was lifted, we used 2 Kirov cranes, but the actual strapping areas, as you can see where the orange straps are here, were on the extremities of 2 of the bearer ends, where the actual crossings would go over each other, which was a little bit of a problem for me because we didn't know what the actual bending moments would have, what effect they'd have on the whole layout. So we had to do some quite detailed calculations to understand how the bending moments of the FFU, and just looking at those without the crossings on as a base model as to how much force and stress that would be put on the actual bearer's matrix, and understand that if the actual bearer system itself could withstand that just from the actual lifting operation. So we found that we got about a factor of safety of about 4, which was quite reassuring when it came to the actual amount of stress that we were going to see in the bearer matrix once the lifting had happened, because this was a 52-ton layout. So obviously quite a lot of force being taken by each of the lifting points. But as you can see, when we actually started, or the crane drivers started lifting it, they were actually with a level playing field. The unit was level as it was sat on these slave rails. But as they started moving the jibs to be parallel with the track, obviously the center of gravity of the layout changed. And this is where it started tilting quite dramatically. And it got a bit more of a severe tilt and list on an angle, which was giving us quite a few concerns as to whether there was going to be some damage made to the bearers themselves as they actually moved it from A to B. But each time they moved it, we had a look at them and checked the bearers themselves, found there was no damage that was obvious. and it's tantamount really to the strength of the material. So it's a very, very strong, durable material, and the proof was obviously with the way this has moved that it caused no damage to the FFU itself, and it's installed successfully, and obviously is running hopefully for another 20, 30 years before we need to look at this renewal again. So as you can see, different positions of the renewal layout being taken to the holding site, which is what the bottom right-hand picture is showing, before it's actually installed in the hole to get it into the right position. And there we are on the top left-hand side, the layout in position with slate panels, obviously, for this East Coast main line, north to south, which is left to right on the picture. And then just a few other snaps showing how it actually was installed. Quite interesting when they started looking at the installation with the Kirovs in terms of how much movement they had to make adjustments to actually get it in the right position. They got it in position, and they were sort of having a staff with coordinates that were taken from the initial layout before they took it out to make sure we got it in exactly the same place. They're asking the Kirov driver to move 12 millimeters at one point, and I thought, well, this is going to take some time. And obviously, asking a crane driver to move 12 millimeters is a big ask with a great big 52-ton layout like this. But eventually, they got it within a few millimeters of what they needed to make sure the alignment was correct. Because obviously, they'd get one chance at this. If they didn't get it correct, the alignment would be a problem in tractometry terms for the next 20 odd years if they didn't actually get it as good as they possibly could. But they did get it within a few millimeters of what they needed, so the alignment is as good as they can get. And there we are, obviously another one from a bit of distance past, just looking at the Kirov cranes doing the drop down of the final position of the layout. The straps themselves weren't actually recovered. We had to cut those off because obviously there's 52 tons of layout sat on top of those, so they cut those off and they're buried in the ballast at the moment for posterity. And there we have the final layout without the cranes over it, just to show you can see what it looked like. Then putting the slave rails in, the transition panels at either end. Then the tamping obviously took quite a while to actually tamp this quite carefully, and clearly the tampers couldn't lift the layout itself. It had just to be tamped to actually consolidate the ballast in between the beds, between the crossings themselves. And there's the final layout before it was open to traffic. So monitoring and following up on the renewal to see what was needed to look at. So we opened the line up at 50 miles an hour as TSR to give a bit of chance for the consolidation of the ballast and everything to settle down, to see where things started to move perhaps a little bit and needed a little bit of remedial work to tighten up. Looked at the crossings themselves the week after the renewal, with ourselves looking at the crossing condition, because unfortunately these were not EDH crossings. I didn't go into the detail about that, but there was a problem with the EDH from Progress Rail being able to manufacture the crossings and then EDH them, which was decided we'd have to install non-EDH due to the issue that needed to be resolved, which was a technical issue with how the actual casting was carried out, and they developed small cracks in one of the crossing noses, so they rejected some of those. So we had to say we'd accept the crossings without EDH, knowing full well we'd have to do some remedial work on the crossing nose because of the work hardening that was needed to actually get them up to a higher hardness level before the steel, the AMS steel, actually stopped flowing due to the impact loading. So there's quite a lot of work needed after that to do some remedial repairs on those. Anyway, there was some voiding that we saw underneath some of the bearers, not surprisingly, because of the settlement that occurred. That was then repaired by looking at visual hand tamping, and then the actual speed was increased to 80 miles an hour for another week. And we looked at how we needed to grind and repair the crossings as far as possible to allow for the fact that the work hardening is occurring. And then after another week, we looked at inspecting them again, and then after that, we were able to actually increase the line speed to 100 miles an hour. So after Robel tamping had been carried out, everything remained quite very, very tight in terms of the ballast movement. So everything seemed to be working quite well, and it's been like that since, as far as I know. The track quality is around about satisfactory at the moment, as far as I know. That's the last I heard, last time I spoke to the TME, which is a good result in terms of the problem we saw from the renewals of past, where soon after the renewal had taken place, the track quality went straight into poor or even super red category. And there we are, the first zoomer going over the layout itself, not long after it was renewed. So thank you very much for your attention. Gone on for quite a lot, so hopefully you found it interesting, but any questions, please let me know. So back to you, Liam.
Thank you, Phil. Thank you, Phil. We have a question from David Philpott, but there's quite a lot of context with it. So could I ask David if you would like to unmute himself, and maybe would that work? Pose the question yourself, David.
Yes, am I allowed now? Can you hear me?
Yeah, we can.
Can hear you.
Okay, Phil. You know, I've done a lot of screed while I was watching that towards the end of it, because I was on site for the 1986 or 88, whenever it was, renewal for the whole time, and David Packer, who I think is also participating in this, was AC Works at Doncaster at the time, who designed and constructed the first lot of Greenheart timber way beams that we had there, and that was a challenge in itself. As you said, they're very, very hard. They planed the tops level on site to get a perfect billiard table finish, and the blades lasted about a minute, and then they had to change them, and so on. You know, but that seemed to be fairly successful. We didn't. There's always been a problem of coach screws breaking, and you know, that might continue. I hope for your renewal it doesn't, because I'm really enthusiastic about these bearers. But I'm not quite sure. You mentioned about the movement breaking the screws. You didn't say particularly what the movement was. We found that we got a clockwise rotation of the crossing due to the direction of traffic on the different lines, and we put sort of ground anchor bars and tied them in deep on each leg of the crossing. Did you do anything like that to try and prevent rotation on this session?
No, what we did, or what the maintenance organization should have done by now, they were going to do it last year, was the 2003 renewal was then ballast glued.
Yep.
So that's what there was no rotation issue with the previous layout. The TME at the time
because of the glue.
was a bit concerned about that, but they were actually ballast glued the new layout as well. That's what they're planning to do.
Right. Okay. So that in effect joins it all together, doesn't it? Yeah. So yeah. I mean, it's really fascinating. So in my sort of working knowledge, it's been renewed 4 times now. It's great to see your modern kit using it, because when we did it, it was very much primitive. We had 2 75-ton breakdown cranes, which were exceedingly slow. We didn't have tilting wagons and that sort of thing, but nevertheless we still managed to do it well inside the 72-hour possession that we had. So great to see your version. One last question, and then I'll let somebody else have a go. Why is the line speed 100, not 125 here on a straight piece of track?
Good question. I don't really know the answer to that, but from an engineering point of view, I think it might be to reduce the dynamic loading on the crossings because of the damage it causes.
Yeah.
But that's my only theory, because we've asked that question ourselves, and that's the only answer I've got from some other engineers.
Well, my knowledge of that is when we did the renewal, it was the old truss girder bridge at Newark Dyke 278 just north of there, and there was a reverse curve between the between the crossing and the bridge that was only fit for 100 miles an hour. It was more than 100 through the station and more than 100 north of there. And then they renewed the bridge and brought it to a standard 6 foot. So, you know, maybe nobody's ever volunteered to put it to 125, but probably in terms of reliability, it's better not to offer it. Thank you very much.
I do get some help
Excellent
with those
presentation.
questions.
Thank you.
You're welcome.
Okay, thank you, David, for that question. We have another question from Paul Richards. His question is, what is the life expectancy of the composite, and are there any particular degradation modes that you need to look out for in future?
That's a good question. At the moment, what we have from Sekisui is an anticipated up to 50 years. The way this actually saying anticipated is that FFU itself has only been installed since, I think the first installation in Japan was in 1980. And what they have been doing since then is going back to the same site and having a review and evaluation of what the condition of the FFU is. And every 5 to 10 years they do that. And they've only had them obviously installed since 1989, I think it is. So they've got about 30 years worth of data. So the last time they actually looked at them was, I think, about a year or two ago. And they were still perfectly serviceable. So they were given another 5 years before they actually go back to inspect them again. So at the moment, they haven't had to take any FFU bearers or sleepers out of track due to their condition. So with that in mind, that's why they've sort of given an anticipated 50 years, because they're not quite sure how long it'll last. As far as the repair of the FFU, what we had obviously problems with trying to drill out core out the holes of the screws that were damaged on the Greenheart timber. If we did that on a normal berry or even in a concrete berry, you could drill out a core, put some polymer into the hole that you drilled out, recreate the conditions for either inserting a screw insert if it's a concrete bearer to reposition that and get that actually working again so it can accept a screw in future. You can do a similar thing with FFU. So if we get some elongated holes in the screws movement, perhaps in time, you can take out the screw. You still actually release it. It's not a problem to actually unscrew it. You can core out that hole if it's too oval or something like that. You can then put another polymer into the hole again to fill it up, and then drill it back into position that you can actually reinstate the screw into position as it was before. So there are processes in place to actually allow that to happen. And if there's any damage to any of the FFU in terms of, say, there was, I don't know, for goodness sake, hopefully not to happen, but a derailment occurred and it damaged the FFU, then again, the same polymer can be used to reinstate the actual FFU condition back to what it was before.
Interesting. So do we have any other questions? I don't think there are any in the chat, but does anyone else on the call have any?
Hi Liam, it's Andy Packham here. I've got a couple of questions.
Not allowed to ask Andy, you know all about this.
Yeah, I know.
Go ahead.
I'm not being deliberately difficult.
No, only joking.
Just one thing, the track bed degradation modelling that was done with finite elements, and showing that the solution you ended up using was 160% improvement with the FFU, the undersleeper pads, and the double compaction, which is really good, isn't it? But I was wondering, is there any monitoring of that over time taking place to see whether that level of benefit realizes itself? Because if it does, it's quite significant in terms of trying to use this in other places, isn't it?
Yeah, definitely it will be. As the only part of modelling, sorry, not the modelling, the monitoring I've got organised is Southampton University went out to do some trackbed monitoring, or in other words, just understanding what the actual performance of the trackbed was before the renewal took place. So what we had in the previous scenario before it was taken out. And being back once to look at what it was like, I think it was about a couple of months after the renewal took place, so everything had been tightened up by then. They were due to go out earlier this year as well, but obviously because of the COVID situation, that put that on hold. So they're going out actually next month to do the second monitoring, and then we'll do another one. I think it's about another 6 months' time after that, so probably May time next year. So that's the monitoring I've organised because I want to understand a little bit more about the performance and how it's actually holding up over the first 12 months. In the long term, maybe we'll consider how we can actually monitor that and do the similar sort of thing a few years down the line with Southampton University doing a similar exercise, but that's not been organised yet. But you're quite right. I think it would be useful to give the region and obviously ourselves as technical authority sort of visibility of what the accuracy of the model simulation actually prove.
Yeah, okay. And I've got a second question actually, and talking about University of Southampton, that kind of takes me into it, because I'm currently working with them on a paper for the next journal of the Permanent Way Institution, which is all about the testing of composite sleepers. And during the discussion, Aaron van Belkom, or I don't know if he's somebody that you deal with, sent it in a picture which showed a bridge, a ballastless bridge, which had sleepers on top of it, composite sleepers on top of it, fixed directly to the bridge. And I thought that was a fairly unusual thing, but he tells me that that's quite a common thing to have on the continent, but in the UK we tend to have longitudinal bearers all the time, which was interesting to me. And the reason I mention that is because you talked about bridge sleepers, and I was wondering if you were talking about bridge sleepers that are directly fixed to the track, or ones that are actually on ballast on the bridge, but are a little bit more less damaging to the bridge because of their nature. I actually sent a little photograph to Liam just now. I don't know if you can show it on the screen. That's the sort of arrangement. Do we have many of these in the UK, do you know, Phil? And is that something that's being looked at?
We do have some. I mean, they look like the side-cut sleepers actually, which are not the FFU version, but a similar composite. Yeah. But basically, we've got some that have got longitudinal beams, like you can see under there, and then there's sleepers that cross those. So they've got transoms keeping those longitudinal beams together, and then you've got a sort of sleeper arrangement as you would think of in plane line terms on top of them. We've got some bridges like that. But the others that, well, I think the FFU has been changed on at least 5 bridges that we had on the trial certificate, which wasn't something I was involved with, but they were in the troughs that you can see on some of the older style girder bridges that hold the beams in that sense. But I think in future we've just got approval and full acceptance for FFU bridge beams to be available for anybody who wants to use them now. We're working towards the same for planeline sleepers, and I think we're looking this next year at the S&C bearers side of things as well.
Yeah, oh, good. Right. Yeah, no, I was just interested to know. That's all. Yeah. Back to you then, Liam.
Thank you, Andy. So we have time for one last question. If anybody has one. No. Okay, in that case, may I ask to go back to you, Andy, for the vote of thanks, please?
Yeah, thanks very much, Liam. Well, Phil, thank you for what was a really, really interesting talk, and it was real sort of nitty-gritty engineering stuff, wasn't it? So much to think about, so much to make sure was in place so that nothing went wrong. And you described a couple of sort of hairy moments, at least in your mind, which were actually fine, which was good. And I can imagine that this must have been on your mind quite a lot before the grand day when everything went in. It certainly would have been on my mind if I'd have been in charge of it all, or had the involvement that you did. A couple of really interesting things. I liked the bit earlier on when you were saying there was a bit of a setback to getting approval for using this sort of technology. And I like the bit where I think it was the RAM had said that I want you to take up the challenge of being able to implement this new technology. And that's what's happened, and it looks like it's going to work out well. And it just reminds us that, you know, in a sense, we have to take risks to introduce new materials and new methods to doing things. But you can mitigate a lot of the risks by really thinking about it, and by having good engineering minds on it, and people who are prepared to challenge it and challenge things and ask the right questions, so that you do end up with success, which certainly seems to have happened in this case. So, you know, going back also into the history of it, there's obviously, you mentioned, a sort of 15 to 20 year renewal cycle for this. So lots of other people have had to have the challenge of Newark Flat Crossing, which is kind of a famous crossing, isn't it, in this country? And it's good that there's so many historical photographs of what's happened in the past and the methods that have been used that we can refer back to. And of course, Phil, you produced a very good paper for the PWI journal in April, which goes through and describes all of this. And I think that will be a reference piece of information for people doing this in the future, and indeed doing this sort of thing in other places as well. So thank you for that. You've been a bit of a star this year for producing papers for the PWI. You were also involved in one in the more recent journal, the October journal as well. So, and I think there's another one coming next year. So thanks for your involvement, and a message to everybody else out there that we at the PWI really like it when people volunteer to write papers for our journal. Usually some really interesting information to share, and it gets your name about as well. So please do as Phil does. But just to tail off, could I thank you, Phil, very much for all the work you've put into making this presentation, to writing the paper in the journal, and for being so good at answering the questions that we had tonight. So I don't know, Liam, if you can unmute everybody, but if we could give a vote of thanks by clapping. The microphones still, yeah, they're coming. If people are able to unmute their mics, and then on the count of 3, if we could give Phil, I appreciate it, Phil. Thank you very much.
Thank you very much.